The control of genes is typically found upstream of the gene. In this case, we've got a couple of operons that are under negative control. Negative control implies that they're going to be repressed or induced through use of the operator. So the operator is immediately upstream of the gene. It could be one gene or an operon in this case. So these are your genes. The operator is located immediately upstream. Bound to the operator, we'll find a repressor. If the repressor is bound, like the bottom, then it will inhibit the ability for RNA polymerase to proceed forward. RNA polymerase is blocked, it cannot proceed. If the operator is open, RNA polymerase can proceed and transcribe as usual. So we call this negative control when we're using an operator and a repressor system. It can either be repressed or it can be induced. The first situation I'm going to show you is a repression situation. This is arginine biosynthesis. Arginine biosynthesis is essential. We need arginine in order to survive, as does E. coli. But if it can find it in the environment, then it doesn't need to synthesize its own arginine. It can just obtain it from its diet. So as soon as arginine is added, we no longer need these particular genes for arginine biosynthesis. In a typical state, there's no arginine, and so the operator is open. RNA polymerase polymerizes the transcription of ARG-C, ARG-B, and ARG-H. If arginine is present, it will bind to the repressor, causing a conformational change. That conformational change will allow the repressor to bind to the operator. Once it's bound to the operator, RNA polymerase cannot proceed, and these genes are not transcribed. The same idea can occur in an induction situation. So here, we typically don't need lactose catabolized because a lot of times lactose is not present. But if lactose is added to the media or to the environment, then we could turn on the lactose catabolizing genes. So in the induction state, it's typically off, it gets turned on. In the repression state, it's typically on, but gets turned off. So again, in the induction model, the repressor is bound to the operator in a normal state. We don't need these genes if there's no lactose. This is catabolism, so the breakdown of a product. If lactose is present, lactose will bind to the repressor, again causing a conformational change. But instead of putting it on this time, it will take the repressor off of the operon, allowing RNA polymerase to proceed forward for the transcription of LAC-Z, LAC-Y, and LAC-A. You can also have positive control of gene regulation. Positive control usually happens upstream of the promoter, not directly upstream of the genes. And this is typically in a situation where the RNA polymerase is not needed very often at all, and therefore the RNA polymerase and its associated sigma factor do not bind well to the promoter sequence. This is maltose catabolism. Maltose catabolism is not often used because E. coli would preferentially use glucose, then lactose, then galactose. Maltose is really far down the line. So the sigma factor and associated RNA polymerase are typically not bound to the promoter because it's not often used. However, upstream of this promoter, there is an activator binding site. The activator binding site can be bound by an activator protein. That activator protein needs again a conformational change to allow it to bind. And in this case, it uses the inducer, which is the sugar maltose, to allow it to have its conformational change to bind to the activator binding site. When it binds, it can allow RNA polymerase to bind more strongly to the promoter and therefore allow it to proceed with transcription. Sometimes we don't just see control of genes under one promoter. Sometimes we see them under multiple genes under the same promoter. So a lot of times we'll see different promoters being activated simultaneously, and this is usually due to similar sigma factors. So if you have similar sigma factors that can activate a variety of genes, then those sigma factors can all bind, allowing for their RNA polymerases to bind. When we have multiple genes and multiple operons under control of the same regulatory region, we call that a regulon. So the regulon is all controlled by the same regulatory proteins, the same sigma factors. This can either be a negative or positive control. It can be turning on or turning off. But it is a global control mechanism that will activate genes throughout the chromosome that are all important for a particular function of this cell.